Hey everyone, Ivan here. Today we're getting to something truly fundamental, the building blocks of all computing, bits, bytes, and binary. If you've been following my channel, I love exploring how systems work from the ground up. With Austrian economics, and now we're applying the same approach to computer science. Here's something fascinating. Everything your computer does, from rendering this video to running complex AI models, ultimately boils down to simple patterns of ones and zeros. That's it. Just two digits create everything you see on screen. Today we'll explore how these simple binary digits form the foundation of all computing and how computers represent everything from text to images to video using nothing but these basic building blocks. Let's get into it. So why do computers use binary? Just ones and zeros, instead of our familiar decimal system with digits 0 through 9. The answer lies in the physical reality of how computers work. At their most fundamental level, computers are built from millions of tiny electronics switches called transistors. These switches have two stable states, on when electricity flows or off when it doesn't. This binary nature, just two possible states, makes electronic components simple, reliable, and cheap to manufacture. We represent this state using the digits 1 for on and 0 for off. Binary is also mathematically elegant. Using just two digits, we can represent any number through the binary number system, perform any calculation, and encode any type of information. In binary counting, each position represents a power of 2 rather than the powers of 10 in our decimal system. So while decimal position represents 1, 10, 100, and so on, binary position represent 1, 2, 4, 8, 16, and so on. For example, the binary number 1011 means 1 by 8 plus 0 by 4 plus 1 by 2 plus 1 by 1 equals 11 in decimal. Even though it can seem inefficient, binary numbers get lost quickly. The simplicity and reliability of two-state systems make binary the perfect foundation for computing. The most basic unit of information in computing is the bit, short for binary digit. A bit can only be two values, 0 or 1. You can think of a bit like a light switch that's either on or off. By itself, a single bit doesn't tell as much. It can only represent two possible states or answer a simple yes or no question. But the power of bits comes when we combine them together. With 2 bits, we can represent 4 different values. With 3 bits, we can represent 8 different values. With 8 bits, we can represent 256 different values. The pattern here is 2 the power of n, where n is the number of bits. Each bit we add double the number of possible values we can represent. For instance, to represent a traffic light, red, yellow, green, we need at least 2 bits since a single bit can only represent 2 states. To represent the 52 cards in a standard deck, we need at least 6 bits, since 2 to the power of 6 equals 64, which give us enough combinations. This concept of using combination of bits to represent increasingly complex information is the foundation of all digital data. In practice, computers typically group bits together into larger units. The most common grouping is 8 bits, which we call a byte. A single byte can represent 2 to the power of 8 or 256 different values, 0 through 255. This is enough to represent all the basic characters we type on a keyboard. The ASCII is the American standard for that encoding. Developed in the 1960s, uses bytes to represent text characters. For example, the capital letter A is represented by the decimal value 65, which in binary is 01000001. As we need to represent more data, we use larger units. 1 kilobyte equals 1024 bytes. 1 megabyte is 1024 kilobytes. A gigabyte is 1024 megabytes. And a terabyte equals 1024 gigabytes. And a petabyte equals 1024 terabytes. To put this in perspective, a single text document might be a few kilobytes. A high-resolution photo might be several megabytes. A 4K movie might be several gigabytes. All the books in the Library of Congress will be around 15 terabytes. All human language ever spoken will be hundreds of petabytes. Modern computers work with these larger units constantly. Your computer's RAM might be 16 gigabytes, while your solid-state drive might store 1 terabyte of data, all ultimately represented as collections of bits. Let's look at how computers represent different types of information, starting with text. The original ASCII standard used 7 bits per character, allowing for 128 different symbols, including uppercase and lowercase English letters, numbers, punctuation, and control characters. For example, the word hello will be represented as H equals 01001000, E equals 011000101, L equals to 110110, L equals to 11011100, and O equals to 111011111. However, the ACCI was very limited. It couldn't represent characters from non-English languages or symbols like emoji. This led to the development of Unicode and encoding formats like UTF-8, which can represent virtually every writing system in the world, plus emoji and other symbols. Unicode uses variable length encoding, meaning some characters take more bytes than others. For example, a simple smiling face emoji requires 3 to 4 bytes in UTF-8 encoding, representing a much larger number in the Unicode system than basic Latin characters. When you type on your keyboard, each keystroke is converted into these binary patterns stored in memory, and they're interpreted by your application to display on screen. Images are represented quite differently than text. The most straightforward approach is to divide the image into a grid of tiny color squares called pixels. On your screen right now, you're looking at thousands of these pixels, each displaying a specific color to create the overall image you see. Each pixel's color is typically represented using the RGB, red, green, blue, color model. We use 8 bits, 1 byte, for each color component. Then give us 8 bits for red intensity, 0 to 255, 8 bits for green intensity, 0 to 255, and 8 bits for blue intensity, 0 to 255. This gives us 24 bits per pixel, allowing for about 16.7 million possible colors, 2 at the power of 24. For example, a pure red pixel will be red 11, 255, or green just 7 zeros, blue 7 zeros, while the yellow pixel will be 6 ones, and so 255, and green 7 ones, 255, and blue 7 zeros plus the 0 to have the 8 bit. The size of an uncompressed image file can be calculated as width by the height by bit depth. So a 1920 by 1080 pixel image, a typical full high-quality image HD with 24-bit color will require about 6.2 megabytes of storage uncompressed. This is why we use compression techniques like JPEG, PNG, and GIF to reduce file sizes by finding patterns and redundancies in this pixel data. Audio is represented by sampling sound waves at regular intervals and converting the amplitude loudness at each point into a binary number. The quality depends on two factors: sample rate, how many times per second we measure the wave. 44.1 kHz for CD quality means 44,100 measurements per second. Bit depth, how precisely we measure each sample. 16-bit allows for 65,536 possible loudness levels. For stereo sound, we store separate data for left and right channels, double the amount of data. This is why a standard audio CD with 16-bit stereo sound at 44.1 kHz can hold about 80 minutes of music on 700 megabytes of data. Video takes this a step further by combining a sequence of images, frames, with synchronized audio. Uncompressed video will be enormous. 1 hour, 1080 video at 30 frames per second will require about 670 gigabytes. This is why video compressions like H.264 or H.265 is crucial, using techniques to store only the difference between frames rather than complete images. When you stream a video online, your device is constantly receiving this compressed binary data, decoding it in real time and converting it back into images and sounds you experience. From the simplicity of a single bit to the complexity of streaming video, everything in computer ultimately reduces to a pattern of ones and zeros. This binary foundation has remained unchanged, even as computers have evolved from room-sized machines to the powerful devices in our pockets. The principles we've covered today are the same whether we're talking about a massive data center or a simple calculator. Understanding bits and bytes gives you insight into how storage works, while sizes are what they are, and how the seemingly magical digital world around us functions at its most fundamental level. What aspects of computer fundamentals would you like to explore next? Let me know in the comments. And if you like this video, please give me a thumbs up. And don't forget to subscribe if you want for the next video in our computer science series, where we'll explore how hardware and software work together. This is Ivan, helping you understand the technologies shaping our world, one bit at a time. Thanks for watching, and I'll see you in the next one.